So we've talked about limits, introduced how to evaluate them, how to look at graphs and determine them. Now we want to turn things over to Wolfram Alpha, start talking about some different applications of limits. Before we get into those though, we just want to go back and cover some simpler problems that we have worked by hand, but just look at how we would evaluate these using Wolfram Alpha to get a feel for how the software works and how we can answer these types of questions. So let's start off with example 1. We're given this function x plus 2, that quantity squared, divided by x squared minus 4, and we have 3 different limits that we want to evaluate. So in order to do this, again, Wolfram Alpha is relatively intuitive, so we can typically just tell it what we want it to find. So for instance, we can tell it we want the limit of x plus 2, that quantity squared, divided by x squared minus 4. So a couple of things to note here. The use of parentheses to make sure we're squaring that entire expression x plus 2. That exponent key, that caret key, is, you get that by holding down shift and pressing 6 on your keyboard. And then dividing by putting that entire denominator inside parentheses. So we just need to make sure that the syntax for that function is correct. So we want to find the limit of that function as x approaches, in part A, negative 2. So once that answer is generated, the first thing you want to do is take a look at this first expression and make sure that this matches what you thought you were intending to put in. So does this in fact say the limit of this function printed correctly as x approaches negative 2? In this case, we've got that all worked out, and it's telling us that that limit is 0. It's giving us a graph of the function to show what's happening, and it's even got that open circle, in this case noted at x equals negative 2, to show that the function's undefined there, but in this case we do have a limit. So in this case, our answer for that limit is going to be 0. So in part B, we want to do the same thing, except now we want to find the limit as x approaches 0. So we can keep the rest of that all the same and just change what x is approaching. So again, we get that limit statement that we want to verify, stated that that limit is approaching negative 1, or that limit equals negative 1, and we have a graph depicting the behavior of the function around that point. So our answer in part B here would be negative 1. And in part C, we want to determine what's happening as x approaches 2. So again, just changing this last number. So in this case, we have that limit statement, which again matches what we wanted. It's telling us that the limit, for the limit, the two-sided limit does not exist. Then it looks more specifically giving us the left-hand limit and the right-hand limit, showing that those are negative infinity and infinity, and gives us that graphical representation of what's happening. So since the left-hand limit and the right-hand limit aren't equal to each other, all we can say in this case, is that this limit does not exist. So if we were asked a more specific question about the left and right hand limits, we could provide those answers of negative infinity and infinity, but in this case we can just say does not exist. We can also look at taking an infinite limit, so we can take the limit of a function as x approaches infinity. So in this case, we need to change our function to be the limit of, in parentheses, 8x plus 6 divided by 3x minus 8 as x approaches, and then for infinity, we'll just literally type out the word infinity. If we wanted negative infinity, we could just put a negative sign in front of that. So again, we want to verify that this statement matches our expectations. Is this the problem that we wanted to answer? In this case it is, and so that limit is going to be 8/3. In our last example, looking at just some of these basic problems that we've covered before, we want to use Wolfram alpha to find any horizontal and vertical asymptotes for these three different functions provided. So again, Wolfram alpha is fairly intuitive. We can just ask it to find asymptotes for the given function. So which in this case in part A is x squared plus 36 divided by x squared minus 36. And actually it looks like I've got one extra parenthesis in there, so I'm going to delete that. Hit this one more time. So again, there's going to be this first box that tells us the input interpretation. We want any asymptotes for this function. In this case, it's telling us that as x approaches positive and negative infinity, our function is approaching 1. So we have a horizontal asymptote at 1. And for vertical asymptotes, as x approaches both positive and negative 6, our function is headed to positive and negative infinity on those different sides. And we've got a graph, again, to kind of show us what's happening. So we have our horizontal asymptote, and we have the two vertical asymptotes represented. So in this case, we have a horizontal asymptote at y equals 1, and vertical asymptotes at x equals positive 6 and x equals negative 6. So in part B, we still want to find asymptotes. In this case, for x to the 6th over x squared plus 6. So again, check to make sure that this input is what you were expecting that function to look like. In this case, we get some information about a polynomial asymptote. We're only interested in horizontal and vertical asymptotes. So even though this is giving us this information about an asymptote, it's not a type of asymptote that we're covering in this class or that we're interested in. So for this type of question, we would just say that none exist. There are no horizontal or vertical asymptotes for this problem. And then for our last problem, we have 4x divided by x minus 7. So again, we can either look at the graph output or look at this information. As x approaches positive and negative infinity, our function value is approaching 4, which gives us a horizontal asymptote. As x approaches 7, our graph is heading to positive and negative infinity from either direction. So we have a vertical asymptote at x equals 7. So our horizontal asymptote at y equals 4 and a vertical asymptote at x equals 7.